All right, perfect. So I apologize that last class was probably a little hectic for you because there was a lot of new information, but then also I was literally teaching from a car that I was riding in on a phone hotspot. So unfortunately, my plane just got delayed a couple hours. So it was everything I could do. I literally got in the rental car at 5 o'clock as the car class was starting. So I made it work the best I could, but I apologize. It was a little haphazard. Um, so today I did just kind of want to start off going over some of the biggest key points from last week. Unfortunately, we only have a few people on the participants right now. I'm guessing just because for some reason people didn't realize that the link would be the same for today. So most of the students that are on right now have previously taken my AI course, or automation integration course. So they're basically going to know all the answers to these questions, but I still want to just kind of have a short back and forth here just to make sure that everybody's on the same page about what we talked about last week as some of like the really, really big key concepts. So let me actually just open a notepad here. So you guys can see this notepad just fine, right? You can't see, am I not
No,
sharing? Or you can?
no, just the
No. Oh,
camera thing.
let me try this again. Now can you see just notepad plus plus?
Yes.
Okay. Um, the first thing I wanted to just reiterate was what is just in a really broad sense. Maybe I can make this bigger. Um, Zoom in. Oh, okay, there we go. All right. So just in a really broad sense, what is a protocol? Like, what would you say is the definition of a protocol?
A procedure how we may use the devices and electronic equipment and anything else.
I mean, I think procedure is an okay word there, but I would even say just in a broader sense, like not even necessarily in engineering. Like what would we consider a protocol? Because I think this is one of those scary words that I like to take away the power of so that you guys feel a little more comfortable with using like the word protocol. So what would be kind of more even a general definition?
Okay. Guide.
What was that?
Yeah. Standards, like standards and guides, kind of a
Well,
definition
yes.
too.
So I like the word definition there. Yeah, and standard. We will talk a little bit about the IEC 61850 standard today, and we'll talk a little bit about why it's slightly different than what a protocol is. Like it actually has protocols inside of it. But yeah, I mean, basically, a definition is a good word. But it's kind of a set of rules for how we can like structure data in terms of engineering. But you can even think about it. You probably heard the term like a military protocol, right? Like that they have a set of documents about like, oh, in this eventuality, these are the actions we're going to do or something. It's basically a set of rules where it gets everybody on the same page, and so they're performing the same actions, right? And so in terms of engineering and when we're communicating, the protocol is it lays out the rules for like if we send 101010, then the other device is supposed to interpret it this very specific way. Because if we didn't have a protocol, we'd basically be throwing ones and zeros out into the world and hoping somebody else understands them. And we don't want to do that. We want to set out very, very clear rules to say, if I send this, you need to understand it this way. But then also, if I send this, then these are the ways you're supposed to reply to me. So there's a lot of different rule sets that are set out and everything there. But protocol, it's a very kind of, as a general term, it's really this agreed upon uh, set of rules for something would be would be a protocol. And then in engineering, we use that generally for making devices communicate to each other because we want a very strict set of rules for that. All right. So then another one here is what is Ethernet? So Ethernet is actually a protocol itself, but what exactly is Ethernet? So essentially, it's a document that's a protocol that lays out how we can actually structure data to make different devices communicate to each other. So it has in the Ethernet document, it actually lays out like things like MAC addresses and how devices should understand those, and that they need to be unique, and then what different pieces of hardware like switches and stuff like that can actually do. So in all of that, none of that says what type of physical cable you need to use, and that's kind of one of the points I wanted to get across here. Is a lot of people confuse Ethernet with physical cabling, and that's not what it is. It's a software level of something, and we can run it on multiple different physical cable types. Um, so if any of you were curious, just this is a little tidbit here that it's something you should probably utilize while you're at UMaine, is you can actually look at some of these standards and protocols, the actual documents where these things are defined for free through the school. So through University of Maine, you have access to IEEE standards and documentation. So Ethernet is actually 802.1q. So it's the IEEE standard for that. So you can actually go to the UMaine website for Fogler Library. So I'm going to just bring up the internet here again. Sorry, I just have to move this out of the way. So if you just go to basically the UMaine library, you can search stuff like I just searched IEEE 802.1q, and you can see there's a result here that's the 802.1q 2018. And they even have one here that's the red lines. So you can actually even see what the changes were from the previous one, or they just have like the actual document. And then you just click on it and you basically log in with your UMaine credentials, and then they give you a PDF of this. And so you can actually download this and keep it. So even after you graduate from UMaine, you can still have these documents that generally, as a professional, these cost many thousands of dollars theoretically, because you have to maintain like an IEEE membership. So it's a good idea to go and look at some of these. But you can see here the 802.1q standard is 3,600 pages long. So I'm definitely not suggesting you go out and sit down and read this whole thing. It's more for like if you run into certain cases and you're kind of curious about it, then you could jump into the document and like Control F for that certain thing. Like if you were curious about like how MAC addresses are defined or something, there's going to be a whole bunch of different things in here. And there's a lot of different keywords and definitions and everything. But more, I just wanted to kind of remind you of that, that when you run into something in engineering, a lot of the times it'll reference IEEE standards or something. You can go and actually look at these standards. And depending on your skill level at that point in time, they're either going to be basically gibberish to you or very understandable. Definitely a few years ago, this would have scared me, but now it's all, I understand everything in it just from that I've run into it in my general work. So jumping back here, so basically Ethernet is a protocol. It's outlined in that document, actually 802.1q. So then anyone that wants to implement Ethernet in their devices, they go and they get that IEEE document, and then they set up Ethernet the way it's described there. And then they know afterwards they can communicate with any other Ethernet device out there. But as I mentioned before, Ethernet is not actually like a hardware standard. Theoretically, it's more of a software standard. So in terms of physical media for Ethernet, what are the like most common ones that we use for Ethernet communications? There are two really common ones we use.
Twisted pair copper.
Yep, that is one. So twisted pair copper, it's usually defined as category cable. So it would be something like category 5, 5E, etc. So yep, that is one of them. And what's the other one?
Fiber.
Yes, fiber optics. All right, and then the last note we'll put here before we jump into some new stuff is what are the biggest reasons why you would choose to use one or the other? So like what are the benefits of twisted pair? Because right, if one of these was better in every single scenario, we would just always use that one, right? So these are two standards or two different types of physical media we run into, and there are reasons you would use A or B in any given situation, right? So what are the big benefits for twisted pair?
Like cheaper and kind of easier to install. And
yes, it is definitely cheaper overall fiber optics have gotten a lot cheaper recently, but even then it's still cheaper for twisted pair. But then, yeah, the other really big one is it's easy to terminate and install. So it's easy to put an end connector onto terminate and install on the physical cabling on twisted pair. All right, so then what's a big drawback?
The distance that you can go.
Yes. Short distances, generally we're limited to around what? This is a number you should always remember.
100 meters?
Yes, exactly. Around 100 meters. There are some versions of twisted pair where you, at certain speeds, you can only get like 40 meters, but those are pretty rare to encounter in our field. That would be more like really high-end, whatever stuff in like server rooms and stuff. In terms of what we run into, it's almost always considered 100 meters limitation. Actually, one other benefit I wanted to drop into twisted pair benefits, there's also power over Ethernet availability. So I wouldn't be surprised if we see some with fiber optics in the future, but for right now, if we want to power a device using our basically physical cable connection, that's really only commonly available through twisted pair. We don't have that option through fiber optics. Short distances, and then the thing that really causes these short distances is basically it's affected by electromagnetic interference, otherwise known as EMI. So those are the good and bad things about twisted pair. What about fiber optics? Benefits. So when would we want to use fiber optics?
If we need long distances.
Yep, long distance is the biggest one for anything outside of the utility world, where it's like if you're in a house, you're going to use twisted pair. But as soon as you leave the house, like running along the sides of the roads and everything, now if they possibly can, they want to use fiber optics. There is some old coax and copper left, but they're trying to avoid that. So as soon as we talk about distances longer than 100 meters, you're basically always talking about fiber optics. Inside like a substation, that's very, very common, is like we have equipment very far away from other equipment, and then we have to use fiber optics. But what's the other big reason that we would use fiber optics in a substation?
Speed.
I mean, it can be high bandwidth. That is a benefit of it. Like if you're talking really, really high bandwidth stuff, then fiber optics at the high end can reach higher capacities. But for most of what we use in substations, actually, fiber optics and twisted pair will have comparable bandwidth availability. We don't have anything inside substations that generally need like 10 gigabits or above. But there's one other really big one that why we want to use it inside of substations. So basically the opposite of this one. It's not affected by EMI. So we can run fiber optics right next to super powerful motors, right next to power lines, things like that. And we don't get signal degradation from it because it's photons of light inside the cable. So then it doesn't actually get affected. So that's the benefits of fiber optics. And that's why in a house, you'll almost always see twisted pair. In a substation, you'll see 99% fiber optics. The other thing is they generally don't really care about cost inside of a substation in those sense. Like they're not trying to save a buck in a substation in terms of like the comparable price between these two. So they're almost always going to use fiber optics. There definitely are some like situations where you use twisted pair, but it's mostly this. And then does anyone know any drawbacks to fiber optics? There's one really, really big one that I just wanted to point out here.
Can't bend it as much, physical.
Yeah, it's very fragile. Like definitely, like you can't bend it, but also even things like vibration, mashing it together, stuff. The internal structure can break down, and then the photons can't get through. Where with copper, as long as copper is touching copper, it doesn't care how tightly it's wound. I mean, there are definitely bend radius limitations for copper, but it's more like longevity, talking about years and years of use, where fiber optics, you just do this once and that cable's done permanently. So definitely the fragility of the fiber optics is a big one, but then it can also be hard and expensive to terminate. So now that's getting easier and easier. We have new equipment that helps us out. But in the past, it was very difficult for just an average person to terminate fiber optics, where with Twisted Pair, almost anyone can go to Best Buy or Home Depot and get some tools to do it very easily. So basically, in terms of SCADA overview from last week, those are the really big points of like things you would just run into really commonly. Then we covered a lot of other vocab. So for those, I would recommend you just go back and watch the video again if there's anything that was confusing. But basically, we talked about like terminology of like SCADA. SCADA is basically as soon as your digital information leaves an IED, right? And an IED was just the general term we used for anything that's a smart device inside of a substation. So we're going to be talking about SCADA a little bit more today, but more actually now into the future of SCADA. So are there any questions about anything we covered last week or anything in this review before we jump into new stuff? All right. So let me put that up. All right. So the title for today's presentation is actually Digital Substations. And that's terminology that's come about relatively recently, where they're talking about substations where we digitize the information as much as possible. So in the past, we've always had substations that were kind of a hybrid model between hardwired and digital. But it was more just like the kind of high level SCADA stuff that was digital, and then all the low level stuff was still hardwired. So now we're working into the point where we actually have what are called truly digital substations, and then we'll see here what actually makes a substation a digital substation. So just a little bit about my background. I realized I didn't really introduce myself last week. I think most of the people on this call still know who I am, but I know there's a few new faces in this class. So basically, I graduated from EET in 2015, and then I got a master's degree at UMaine as well in computer engineering. And then while I was doing that, actually, like while I was getting my degrees, I did high-speed robotics. So I would travel around the country and work in different car factories, setting up different robots to build transmissions. And so from that kind of background, I was basically traveling around a little too much for work. I would go different places for like 3 months at a time. And I decided I didn't really want to travel that way anymore. And so then I came back to Maine permanently, basically. And I started contracting in the power industry and I started teaching at UMaine. So I developed my automation integration course and I taught full time as well for a year at UMaine. But then I also contracted a couple companies. One was now it's ECI, but at that time it was Casco, and then also RLC. But now I'm currently at Omicron, and my job title is actually application engineer in IEC 62850 and digital substations. So that's why this presentation today is basically, it's my background. It's what I literally do every day for my job. So I'm not necessarily a traditional SCADA engineer at this point. So I very much focus in 62850 and digital substations, but my background before this was in SCADA. And that's why I'm pretty suited actually for this job role is in the past, they would have a lot of protection engineers doing this type of stuff. But the problem is we kind of have this weird overlap or lack of overlap actually, where the people that are doing SCADA don't understand enough about the power systems. The people doing the power systems don't understand enough about like networking and SCADA. And then we have this weird thing in the middle that is digital substations. So that's kind of, I'm trying to bridge the gap basically between protection engineers and SCADA engineers. And just a little background about Omicron, it's a company that makes testing equipment for the power industry. So that's everything from relay testing at really low levels, like injecting voltages and currents into relays, to really high voltage equipment that injects into your primary equipment. And you can test transformers and your actual cables. You can test circuit current transformers, basically everything in a power system. The company I work for makes testing equipment for it. So a little bit of history before we talk too much about the digital substations. I want you to realize where this stuff came from. And I'm hoping at this point in the class you've already seen a little bit of this. So definitely jump in if this is already pretty well covered. But essentially, we have a couple different types of protection equipment out there in the power industry. And so the oldest stuff that's still in active use is actually electromechanical based protection. So many of you have probably taken the PLCs course at UMaine, and in that course you used ice cube relays. And so this is basically what we're talking about with electromechanical based relays. So essentially the electrical concept for it was that you had a little arm that was on a pivot, and then you have these contacts that get either connected or disconnected when this arm is pivoted. So you have these contacts over here. This is actually where your electricity would be connected on the normally open, the common, and the normally closed. So if the energizing coil is not energized, then the normally closed would be connected to the common. And then if you energize the coil, then the common gets connected to the normally open connection. And with that, you can create logic, basically. And so what we did in the power industry is you would basically just have this energizing coil based on whatever factor you want to control. So for example, you could just make it so your energizing coil was monitoring the amount of current on your power lines. And if the current ever passed some threshold, then you know you're in a fault condition, like either people are using too much energy and you're going to burn down the conductor, or a tree fell on the line and it's sucking a ton of current to ground, something like that. But regardless, you would have a lot of current, and then that large amount of current you would basically use to energize your coil, and then that could open your circuit to stop energy flowing. And definitely, it's a little more complicated than that. I'm dumbing it down to the very bare bones here, but that's basically the idea behind an electromechanical relay. So that's what they did a long time ago. But it's something you'll see in the power industry is it's a very, very slow moving behemoth. And so this is stuff that was installed in the 60s, 70s, and we're still using it today. So, I mean, I have some notes here on, I was going to ask you guys a question, but I guess I already have it written down here about why we actually still have that stuff out there. But one of the reasons is just cost concerns. And I mentioned that before, where they're not necessarily cost sensitive about choosing between like twisted pair and fiber optics. They're going to choose the better one, even if it's a little more expensive. But when I talk about cost concerns to update, I mean literally a substation replacement costing millions of dollars. And so they don't necessarily want to take down a substation that's functioning perfectly fine theoretically to replace it with newer stuff unless they really, really see a cost benefit to it. And so there's this other aspect here is you cannot take system downtime to replace it. So in some cases, we have electromechanical relays running a substation that's like absolutely vital, and we might want to update some parts of it. Like the electromechanical relays are better ways to do it now, which I'll show you in a minute. But as of that point, it's working well enough. And so they don't want to completely remove the substation and take like 6 months of downtime to replace it with a new one. And when I say 6 months, I mean that's like absolute minimum of the teardown and build back up. Generally, it's going to be even significantly longer than that, especially now we have very long lead times for equipment. So that's another reason that you'll still see this stuff out there, even though it's bordering on 50 years old at this point. One of the biggest difficulties we have with using electromechanical relays is we don't have good availability of data from these. So I wouldn't even really call these IEDs at that point. I would call them electromagnetic relays because they don't have real intelligence built into them. They generally won't have the ability to like plug in a serial cable and get the data out of it. So we don't have visibility of like what is the amount of current it's currently sensing or what is the voltage. And so if one of these electromechanical relays trips, then we know something went wrong, but we don't necessarily have all the data around it to look into to be like, okay, why did it trip? and what can we do to stop that from happening in the future? Like, was it just a nuisance trip? Like it was accidental, something was programmed wrong, or did we actually get too much current on the line? Something like that. So generally, when we're talking about electromagnetic relays, that's one of the other really big issues nowadays is there's absolutely no data we get out of them. They also require a lot of manual settings and adjustments. So this might not be something you think about as an engineer because you generally design something to be correct, and then you send the plans out to build it. You're like, okay, this is the optimal way to build this thing. Now you guys implement that. The problem is, if you don't think about some of these things, like the manual settings and adjustments, you can forget how difficult it is to actually implement your design. So that's another problem with these electromechanical relays is you would put in the prints or something to say, okay, all the set points of these electromechanical relays need to be this exact number. And then a person actually needs to go out and set those correctly and test them and everything. Where with a newer microprocessor based relay, which we'll talk about in a second, you actually have software where you design everything and then you load in the settings. And then you know what's in that relay is exactly what you designed. So there isn't like that human error factor. So that's another kind of big issue with electromagnetic relays is that idea that basically there's a human that's kind of doing the best job they can from the prints, but they could do it incorrectly. So now we've gone on to using microprocessor-based relays. And so if you go into the basement of Barrows, you look at the relay racks, this is exactly what you're going to see there. So any questions at this point about electromechanical relays before we move into microprocessor-based? All right. So microprocessor-based relays are basically our current standard. And so what really changed with a microprocessor-based relay is we started doing something called analog to digital conversion. And so analog digital conversion means you take something like the amount of current that you have on the line, and instead of sending it as a analog value, like in this example right here, where if the current goes too high, then it actually directly energizes this coil. Instead, with analog to digital conversion, we take the amount of current or the amount of voltage and we convert it into a digital representation of that. So something that's ones and zeros, and then we can send it into a computer to actually make decisions based on the ones and zeros. And so that gives us the ability to add a bunch of additional logic into these protection settings. So that's what we currently use on the back of the relays. You can take a look at them. I don't know if I can zoom in as part of the slideshow. I hope you guys can see this okay, but yeah, it looks like I can't zoom at all. But basically, this is what the back of one of those relays would look like. And we have a whole bunch of different types of inputs on here. So the ones you would have seen back, even on the oldest microprocessor-based relays, are these different kinds here where they're the kind of physical contacts. I'll talk about these different communication ones here in a minute. So with these physical contacts, we have some that are binary I/O, which I'll talk about in a minute, and then we have some that are currents and voltages. So here we have voltages, and here we have currents that are connected. So with the currents and voltages, we just take our signals coming in from the power system, we tie them onto these data points or onto these connection points, and then this relay has a computer inside of it where it converts these actual values into ones and zeros, and then calculates things like if you have current that goes to this level for this amount of time, then we're going to trip a breaker. And so when it says that we want to trip something, it uses one of these physical outputs. So basically these contacts, when the computer program inside of this makes that decision that it, like, okay, we're in a state where we need to do something, then it would close one of these contacts. But then it also has these inputs here where if it's reading the state of something that's physical, like the state of a breaker, if it's open or closed, it can be tied into these so that the computer inside of here actually knows what the current state of it is. So these have become very, very intelligent devices. So this is where we came from. That's what we were doing in the 70s. And then this is what we've been doing since probably I'd actually have to ask Paul about when we started really doing this, but my guess is probably mid 80s is when these started being actually like implemented in power systems. But I'm showing you an image here of an SEL relay. It's not to say that this is the only brand that makes protective relays. There's different ones that operate basically on the exact same principles. The reason I have an SEL relay on here is they control like 95% of the market in the United States. Or maybe they did a while ago. I'm guessing now their market share is down a little bit because there's a lot more competition in the market. The reason they were kind of dominant is they were very, very cheap compared to other manufacturers at the time. But when I say very, very cheap, you still have to get a frame of reference for this type of stuff. So a lot of these relays would be in the range of like $5,000. And something I do like about SEL is they're very upfront about their pricing. So you can actually look up a relay like an SEL 421. You can just go to Google, type in SEL 421 Schweitzer. It'll take you to their website, and you can actually see what the price of one of these would be, and you can see what protection functions it actually has. The same cannot be said of these other ones. You'd have a much harder time finding the prices generally. But back in the day, the ABB Hitachi ones or Siemens or GE relays, generally they were going to be like 2 to 3 times the cost of an equivalent Schweitzer relay. So that was, and then Schweitzer had a really, really good warranty. And so that's how they like took a huge portion of the market. Now, like I said, other people are battling it back. I just kind of brought up that point because sometimes people think of protective relays as very like literally these blue boxes, and they shouldn't think of it that way. Like it's a generic microprocessor based relay. It's taking voltages and currents and making decisions based on that. That's basically what its goal is. So nowadays, one of the biggest reasons we like using microprocessor-based relays beyond the ones I've already kind of talked about is the availability of data. So when we have like monitoring systems where we want to look at over time the amount of load usage, or if we want to like see when a certain fault actually happened, we want to look at all the data and understand why did that happen. All of that data generally was originated in these relays. So they actually took in the voltages and currents on here and then stored it into files that in the industry we normally use a file format called ComTrade. So these IEDs would store it in a ComTrade format. We can grab that data out, and then we can make like nice graphs and everything that show when the fault happened, what all the waveforms looked like, and we can kind of back calculate like why did that actually happen. So any question on microprocessor-based relays or them versus electromechanical? Or is all that clear? Okay. So this is an important distinction because I want you to kind of understand what it means for information to be digital. So with electromechanical relays, really nothing was digital information. And then as soon as we move to microprocessor-based relays, basically everything is digital, and that's what enables us to eventually have digital-based substations. So in the future, we have these terms here, digitalization and digitization. So I know those sound like they would be basically the exact same thing, but they're technically not. This is not going to be on a test or something. It's just something I did want to mention here. So digitization is something we've been doing for a long time. So that's something where we convert analog data into a digital format. So we take our current waveforms or our voltage waveforms and we plug them into the relay that converts it into our ones and zeros, and then we do different things to it through SCADA. That would be the digitization. But what we're talking about now is digitalization, which is where we're utilizing more digital technologies in substations in general. So we're trying to remove more of like the electromechanical components and basically just use more digital technologies in general. Anytime we can eliminate something that's like hardwired or a manual operation. So we currently do digitize a lot of information, but we're not necessarily very efficient about how we actually utilize that. And you'll kind of see that over the next few slides. All right, so here's the first kind of example of what you will see when we're transitioning to digital substations. One thing I do want to impress on you though here is that digital substations are something that we will encounter more and more in the future. But right now, in certain places, it's not necessarily there are a lot of field engineers and everything who don't really like the idea of digital substations. And mostly it's because all their training has been on conventional substations. and they haven't really gotten an opportunity to work with a lot of digital substations. Still something that's very, very new to them. So I do just kind of want to warn you that if you go out into the power industry, if you do bring up digital substations or 61850, there's plenty of people that are going to give you pushback on this type of stuff, where they're going to even say things like, "Oh, that'll never work" or whatever. But usually those people are pretty close to retiring, and this is something that is absolutely coming. And it's been a little bit of a slower rollout than I thought it would be, but we're seeing more and more like actually implemented digital substations now. So this, in my opinion, is a really good breakdown of what is a digital substation versus a conventional substation. So when I say conventional substation, I mean like what has been out there for the last 30 years. Like when we built a substation, this is what it looked like. So does anyone know the terminology, the primary and secondary? Would anyone hazard a guess about what separates primary and secondary equipment or data in a power system? That is a very important term for you guys to know. All right. So it seems like it's pretty new to most of you. So that's fine. I was just curious if you guys did know that terminology. So we very commonly separate our power systems into primary and secondary technology, or primary and secondary voltage and current. Sorry. So in this image at the top, you probably understand what's going on here. That these are power lines, and then we have measuring equipment over here. So we have current transformers, which allow us to read the amount of current on the lines. We have voltage transformers, which allow us to read the amount of voltage. And so when that goes through, the information goes through the current transformer, the voltage transformer, it comes out as a much smaller signal than what was put in. And that's actually a really good thing, because basically that means we have our different monitoring equipment in the conventional substation. A long time ago, that would have been electromechanical relays. Now we use it as it's going to be microprocessor-based relays. But because we have these primary values and then secondary values, we can run our secondary values into the substation or into the control house, where then a user can kind of work with them directly. And these are values that are much, much less dangerous to work with, but are also easier for your equipment to work with. So I'm just going to jump back a couple slides and I'll come right back here. So why that might be important is we would be tying secondary values onto these connections right here. If we tried to do this with primary values, then this relay box would have to be way bigger just to compensate for the safety challenges that would go along with that. So when I talk about like primary and secondary, I'm talking like primary is up in the like kilovolts, and our secondary is in the tens to hundreds of volts. And then our currents, again, are in the like amps versus hundreds of amps. So we're talking about values that are significantly stepped down, but they're proportional. So our secondary values are what would be tied into these, and then our primary values are what is out here at this point. That's what's actually being like utilized on the power grid. So that's something that's very nice and helps with safety concerns, but it doesn't make things 100% safe. So I know a couple of you have had some experience in the power industry here. Do you know what one of the biggest safety concerns is working with relays if you're doing anything like isolating a relay? Is there anything that you're taught every time for dealing with relay safety?
The CT inputs
Yes,
are
exactly.
very dangerous. Yep.
Yes. So a CT, a current transformer, is essentially an inductor. And an inductor can become charged with energy, basically. And so if you open the circuit that a inductor is on or a current transformer is on, then it's going to try to maintain the voltage there. And so what happens basically is you open the connection, and it's going to create an arc across the open air there, and that's going to create something that basically burns you or can even electrocute you. So basically, they always tell you when working with relays, never open a CT. Basically, what you do first is you actually short it to discharge any potential energy there, and then you can actually work with the relay. So that's one of the big safety concerns, and that's actually on secondary values. So just because we're talking about like primary and secondary, doesn't mean that this stuff is not dangerous at all. Like the secondary is not dangerous at all. It just means that it's less dangerous than the primary. So you can still absolutely get injured. It's just less likely. So the difference with a digital substation, so what we're looking at down here, is that instead of taking the secondary values back from the equipment, like the CTs and VTs, back into the control house with these hardwired signals, instead we convert them into digital signals out in the yard and then bring back digital information into the control house. So that's, for one reason, that's very nice in terms of you're going to have your people inside of this control house here. They're not going to get hurt by the ones and zeros, right? So in terms of safety concerns, that's already a pretty big benefit. But can anyone else, just from looking at this, can you think of any other potential big benefits that we could have for digitizing the information out in the yard versus digitizing it inside of the control house?
Wiring.
Wiring. And this is not just wire that we're like running out in the open, like in a channel hanging above head or something like that, that's really easy to work with. Generally, this is stuff that's going through conduit in the ground. And so if one of these cables breaks, or if it or generally you're gonna have a ton of cables, it's really a pain to work with because you have to actually physically dig into the ground, lay conduit, and for every single wire, I mean, that's you're greatly increasing your costs. Where if we're talking about a digital substation, one wire can carry the information for basically all of our equipment. We wouldn't do that because of redundancy. We would use multiple wires, but even then, it's a lot less physical wiring that actually needs to be maintained. So that's, along with the safety, that's the other like really big benefit of digital substations, is your implementation costs theoretically can be significantly lower. And there have been some utilities that have kind of released some documentation on what has changed in their cost structure from doing digital substations versus conventional, but we don't have a ton of data on that. But in the long term, we're going to see a big change, I think, in the actual costs of implementing a conventional substation versus a digital substation, because of a lot less wiring needed. So like physically landing cables, things like that, it's going to be a lot less conduit. But then you'll also notice here, there's a lot less floor space taken up by the actual IEDs themselves. And that's basically because we can transmit a lot more information on a single cable rather than needing to land a whole bunch of cables onto a relay. So if I jump back again here, with this relay, basically what we can see here is current for our A phase, B phase, C phase, and neutral, and then our voltages for A, B, and C. And if we wanted to monitor multiple buses or multiple lines at the same time, we'd need multiple of these inputs. With a digital relay, we just send all of it over one fiber optic connection. So one relay can be monitoring 30 current transformers or 5, it doesn't really matter. It's just going to be one cable. Where with a traditional microprocessor-based relay, we would need physical landing points for each of the CTs and VTs it wants to monitor. So that's another really big benefit, and where you'll see like a lot smaller footprints for digital relays. But I'm giving you kind of like, these are the good things about them. But again, there's a lot of pushback right now from industry on actually implementing this. So can anyone guess why we're not just like, basically from everything I've just told you, right? They should be better in every single way, right? So why haven't we seen a ton of digital substations actually implemented?
Can we use the conventional equipment in digital system?
A lot of relays support both. So you can have both conventional signals, like secondary hardwired signals, and digital communications built into them. But they do have newer relays that are only for digital substations where they don't have any physical inputs on them at all.
Would that then
Yeah,
mean there would need to be protection grade, metering devices out by the CTs out in the yard?
Yes. So those are called emerging units and process interface units, depending on if you're actually working with like the breakers and stuff directly on them. When we talk about signals here in a second, I'll talk a little bit more about that. But yes, you do actually then you still need to do the analog to digital conversion. And so the difference is
Mhm.
instead of doing the analog to digital conversion inside of the conventional in the control house, you're now doing it out in the yard. And so you do need specialized equipment out there. That is a cost concern for sure, but theoretically that should be offset by this the savings on just using the single digital line. So
Right.
basically, the big reason we haven't seen a lot of implementation is actually just from people from industry knowledge that we don't have a lot of people out there that actually have the knowledge of implementing the networking and like merging unit side of this and everything, where it's still so new technology and they've been doing certain things a certain way for a long time. We need to design these new substations very, very quickly. They don't have time necessarily to learn the new technology and roll it out. So that is actually it's really just the industry knowledge base, I think, is actually the biggest limiting factor. The other one has just been like equipment availability and costs. So up until now, if you wanted a 61850 based relay, which would be for digital substations, it would generally be more expensive than your conventional equivalent. So that was also kind of holding people back, is there was a cost concern. I think that's basically kind of evened out now. Probably if you're buying a digital relay versus a purely digital relay versus one that accepts hardwired inputs, you're probably going to come out pretty on par with each other cost wise. In the future, the digital equipment should get even cheaper. But I'm surprised we haven't seen a stronger rollout yet of the digital substations, just because I do think there are a lot of benefits. But again, I think really the big issue right now is industry knowledge.
Can we
Mhm.
monitor the digital substation from home?
Yeah, which I mean, that wouldn't really be a concern or a difference between conventional and digital, because in both cases, the information is becoming digitized at some point, and we could still send that over a remote connection. So whether it was with a conventional substation or digital substation, that data would be available to the like overall control center or remote access, anything like that. It's more just the difference for digital versus conventional is actually it's from our secondary level, which wouldn't be data that's sent out.
Yeah, thank you.
So I do want to kind of get a little vocab here across for the actual signals that you would see as being digitized. So we generally group our data into two types of information. So we have binary and analog signals. So binary would be something that is basically on off. It gets a little more complicated than that because we have like double bit binary stuff, but we don't have time to get into that today. But something like a breaker can be open or closed. And so we would consider that binary information, or a circuit switch would be open or closed. Analog information would be something that has a whole bunch of different values it could be. So your voltages and currents, they're not just going to be 0 volts or 1 volt. They could be 1.239 volts, or they could be 1,338, whatever. So an analog value has this whole range of possibilities for what it could be. So generally in the power industry, we use the terms binary inputs and binary outputs. So a binary input would be something where we're like reading what is the current status of a breaker. Is the breaker open or is the breaker closed? And then a binary output would be us telling something to do something or telling something else the status of something. So if we wanted to control the breaker to tell the breaker to open or the breaker to close, we would use a binary output. Um, so the analog information is just going to be the representation of what that current or voltage is on the line. And obviously for a protective relay, that's really, really important information, right? We need to know how much current there is so that we can make our decisions. So if we have too much current, we open a breaker and we stop electricity from flowing, basically. So the reason I bring that up is because these types of things were actually what we did not digitize in the past. So if I jump back here, so the information I was just talking about, the binary inputs and outputs, and then the analog waveforms, that would be the stuff that's actually being sent on these pieces of copper out into the yard. So then here would actually be our circuit breaker or our current transformer or voltage transformer. All of that would have these old like hardwired connections. And so then with new digital substations, our goal is for all of that to be digitized. So I'm going to even jump back another slide here, the microprocessor-based relay. And so this is generally how I even explain it to people in industry, because it's something they still haven't quite grasped, is really the idea with a fully digital substation is you actually have methods of eliminating basically each of these connection types. So we have binary outputs, that's this line up here, and then we have binary inputs, which are the ones just below the fiber optic connections here. And then we have our analog inputs for our voltage and our analog inputs for our current. So we have methods now with the digital substation of eliminating all of those physical connections. And so with a purely digital relay, literally the only connection you actually need at that point is a network connection. So either fiber optics or twisted pair. And so that's something that's very nice. And that's generally how I've kind of explained it to people in the industry, is like we're eliminating these physical connections when we go to a digital substation. So the method of how we're actually doing that is 61850. So you've probably heard that term thrown around a whole bunch at this point, but nobody's ever really cleanly explained what 61850 is. So 61850 is actually a standard. So it's something that's even larger than what a protocol would be, and it actually contains multiple protocols inside of it. So the 61850 standard has 3 different communication protocols: MMS, Goose, and sample values inside of the standard. So originally, the term 61850 was described as a substation communications standard. Over time, they realized that it's something that was used even outside of substations. So then they actually changed the naming scheme to say system instead of substation. So for example, they have configuration files that used to be called substation configuration language. Now it's called system configuration language. But the standard is really, really big. So if you went in there and tried to read it, unfortunately, it's not available on the UMaine Fogler website because it's an IEC standard, which is European. We don't have access to that through UMaine. IEEE standards we do, which would be the American equivalent. But basically what 61850 actually lays out is a lot. So it describes like different data types. So how you would represent a voltage or current in ones or zeros, same with like a binary value in ones and zeros. But then even also how would you represent a circuit breaker as ones and zeros? So that's all in there. It has standards for how to synchronize different relays together in terms of time. And then even has like guidelines for how are you supposed to test if your relays are even working properly, different file formats, how to set up your network so that even you don't have like a single point of failure. There's like a whole ton of stuff in like this is, I'm not even describing all of it. There's a lot in the standard. But what we're going to kind of break it down to today is the protocols that are contained in there. I think that'll make a little more sense for you guys. So there's these 3 main types. And essentially, what we've done for a long time is client-server communications. So that's the SCADA stuff that I've been talking about, where we send information out to like the control center. That in America, we've done that with DMP3 historically. In Europe, they've done it with MMS. 61850 uses MMS inside for the like overall SCADA communications. So at that point, we actually haven't changed anything from a conventional to a digital substation. That's something we've already been doing for a long time. The ones that are different for a digital substation than a conventional substation are these 2, Goose and sampled values. So essentially, Goose is for replacing binary signals. So that would be the things like the your breaker control or your breaker status. And then sampled values is for replacing your analog hardwired. So instead of needing a hardwired cable for your voltage or your current, now you would send it with a sampled value stream over an Ethernet-based network. And the same with the Goose messages are sent over an Ethernet-based network. So these are the really 2 big things that make 61850 61850, and that's what you would be sending on this cable right here. So this underground cable, that's that single communication cable, that would have goose and sample values messages. So the goose messages would come out and tell a breaker to open, or would be from the breaker telling the status. And then the sample value streams would be coming from the current transformer and the voltage transformer to show what the current waveform looks like for those electric values. All right. So with this, though, there are some concerns about that. I've given you a very rosy picture at this point of digital substations, that they're basically perfect in every way. But there are some difficulties that you run into with digital substations, and there are things that we have overcome. We have the technology to defeat any of the issues. It's just, again, people are kind of worried about, they don't have the knowledge yet of how to implement these things properly. So one of the big ones is actually time synchronization. So I have a chart here in just a second. This will make a little bit more sense. But this is a really, really big aspect, actually, of digital substations and something people generally have problems with. So there are basically 3 different scenarios you can run into. So devices can be not synchronized, locally synchronized, or globally synchronized. So when I say that, I mean in terms of time. So if you have like relay A, and I'm sorry I don't have something to draw on. I think this would make a little more sense if I was drawing it out right now. I just don't have a touch screen on this laptop. If you have relay A and relay B, if they were not synchronized, they don't both have the same concept of time. So they both can have a clock internally to say like 1 second has passed. It's just they don't necessarily both know it's exactly 12 o'clock at the same time. One might think it's 12:05 and one might think it's 12:01. And so the problem with that is if we want to compare data between relay A and relay B, if they think it's different times, then for continuous data, then you actually would end up having an offset. So anything like a voltage or a current. And again, I'll show you that on the next slide here. But that would be an issue if they were not synchronized. So then there's the term locally synchronized. So that means if you have relay A and B in the same location, they can talk to each other and agree that it's 12:01, but that doesn't necessarily mean it's actually 12:01. So they could both agree, hey, it's 12:01 right now, even though it's 12:05. That means they can compare data against each other, but they can't compare data against things outside in the world. So the ideal is for everything to be globally synchronized. And that would mean for everything to have the exact same concept of time. So every device that we possibly would want to work with, they all know it's exactly 12:01 right now, something like that. So when we have digital information, the devices need to be time synchronized to be able to compare that information. So if let's say 2 devices have a voltage waveform and they want to compare the 2 voltage waveforms against each other, if one thinks it's a few milliseconds in the future and one thinks it's a few milliseconds in the past, when they compare those waveforms, again, there's going to be an offset. And then if they try to calculate something like a differential current, so one minus the other one, then the values aren't going to be correct. And so when we're sending data over a network, we don't always send data with the same amount of latency. So we can't just rely on sending data for the other device to understand when it was sent. Because if we send like a sample of a waveform at time equals 0, it's going to get to the other relay at like the first time it'll get to the other relay at time equals 5 milliseconds in the future. The next time it'll get there 7 milliseconds after or 3 milliseconds after. So we can't just like calculate against the latency to say, oh, this is always going to be the difference. That doesn't work. So when we're worried about comparing analog waveforms in terms of protection, the worst case difference in time that the 2 relays can have is 1 microsecond. So hopefully that's blowing your mind a little bit, that's a very small amount of inaccuracy that would cause problems. So basically, if relay A thinks it's 1 microsecond later than what relay B thinks, we can't use those for protection in a digital system. So we have to have these devices synchronized to better than 1 microsecond of error. So how I have a slide here just to kind of make sure we get that point across, is basically if we have this waveform, so this is what relay A understands the current to look like, and then we have this other waveform, which is what relay B understands the current to look like. then if we subtract those two, ideally we would get a certain value. And we do that very commonly in protection. So just for an example, if we have a transformer, we might do what's called like transformer differential protection, which we take the current that goes into the transformer and we subtract it from the current that comes out of the transformer. Ideally, that's zero. It's not going to be zero because there are going to be some losses inside the transformer, but ideally it would be zero, that we have the same amount of current going in as coming out. If we ever got a large differential value, we know there's a problem inside of the transformer. So we like set up a set point to say like, okay, as long as it's under this amount of error, then the transformer's fine. If it goes outside of this, then we have a problem. So if relay A thinks this is the current and relay B thinks this is the current, we have this phase shift between them. And you can see that gives a differential value when we're subtracting them at any certain point in time. So the time error can be a certain amount. That's basically that 1 microsecond. So if we're looking at a waveform like this, in terms of power on the United States power grid, it runs at 60 hertz. So that would be 16.66 milliseconds per cycle. So one full cycle of the power or the signal here would be 16.66 milliseconds. We're saying that can't be offset by more than 1 microsecond in either direction to compare it against this other one. So it'd be a very, very tiny fraction of this that it's allowed to be offset. So are there any questions on that? I know we went through it kind of fast, but I know we're running out of time here. So any questions on synchronization specifically? Okay. So with digital information, it's really important that we have synchronization. So relay A can compare information against relay B, basically. Or we can compare information from current transformer 1 and current transformer 2, whatever. So how we actually accomplish this is something called precision time protocol. I don't think I actually have it on the slide. I should have. You might want to write this down. It's the standard IEEE 1588, which is again something you can probably get on the Fogler website there. So IEEE 1588 is also called precision time protocol, and it's essentially how you can attach devices on a network and synchronize them accurately to within 1 microsecond. So that's something that's required for digital substations. So for a conventional substation, we use something else. We use something called IRIG-B or PPS. The problem with both of these is you actually have to run a specific coaxial cable to each relay that you need to synchronize. So I'm going to jump back a few slides here to the microprocessor-based relay again and show you that connection. See this connection right here? You guys can see my mouse, right? Hoping.
Yes.
Yes. Yeah. Okay, good. So this connection right here that's labeled IRIG-B, that was for time synchronization in the past. But IRIG-B, you can only get accuracy around like 1 millisecond, which we need much higher accuracy than that. Theoretically, we can play with some things to get higher accuracy, but instead we use PTP. So again, that's something we can eliminate with a digital substation. We can use PTP, which is sending time signals over an Ethernet network. And so then we can use these same connections that now we're using for all of our replacements of our hardwired inputs. Our sample value streams, our goose messages, all of that comes in now over just our Ethernet connections. So we can eliminate literally every single connection on the back of this except for our Ethernet, which is really, really nice. So time synchronization, though, it is difficult to set up properly for people who don't understand it. So that's, as training will happen, people understand precision time protocol better and will have less problems with it. But this is technically where a lot of people are having problems implementing digital substations. So if you set it up correctly, you can have accuracy to greater than 1 microsecond for all of the relays or all of your IEDs that are connected to a time source on your Ethernet-based network, up to 16 hops. So when I say a hop, I mean like a network switch would be 1 hop. So you could connect one clock with PTP onto your Ethernet-based network, and you can distribute it out to a whole bunch of different devices. And it can, as long as the signal goes through less than 15 switches, then everything is synchronized to whatever the clock is saying what time it is. So I think, okay, I don't have it on the next slide. So how we actually gather time, or how we synchronize the time, is using GPS signals. So you just synchronize your clock to GPS, so then it knows what time it is, and then it just distributes that signal on your network with precision time protocol. So we use this for digital substations because it meets our 1 microsecond of accuracy. So again, this is replacing some of our hardwired connections. On a relay, it's another nice benefit. And then jumping kind of into the next topic, we only have 5 minutes left here. I'll have to cover some of this at the beginning of the next class, I think, just because we don't have too much time left here. But I did want to mention that now, when we're talking about all of this, your network becomes critical infrastructure. So I'm going to jump back a few slides again here to kind of explain this better. Is in the past, if you had a conventional substation, if your Ethernet network went down, it wasn't the end of the world. It wasn't good. You need to get it back working, but it's not like your company's not losing a ton of money per minute while it's down. So basically, if your Ethernet network went down with a conventional substation, you lose your connection going back to your control center, and it won't understand what's going on with that substation. You can't send like remote operation, but your protection is still working fine. So your IEDs here that are monitoring like your amount of current, voltage, and everything on the grid, those are going to operate just fine. And if you have a fault, you have too much current, it will still open the breaker. Everything will work just fine. In a digital substation, if your Ethernet network goes down, you lose protection, which is like the absolute worst case scenario for a utility that they do not want to happen. So that's, again, one of the reasons it's slow to be adopted is that now you've put your critical infrastructure on an Ethernet-based network, and it has to be able to just never, ever have a failure. Like it cannot go down at all. So that's kind of the point I have here on this slide is we actually have methods of making it so that our Ethernet-based networks will not go down. So we have a couple different options. The older method that we used to use is RSTP. The problem with RSTP for network healing basically is that it takes time to heal. And so I already said that, right, that your protection cannot go offline. Like utility will absolutely be losing money if that happens. Then with RSTP for network healing, like if your Ethernet network was to have a fault, then you would be down for about 10 milliseconds, which doesn't seem a lot, but that's unacceptable. So we need to do something better. So instead of doing that, we do these new things called bumpless loss redundancy, which basically mean that you don't lose any network frames when you have a failure. And I know that's a concept probably outside a lot of your comfort zones, just in terms of understanding networking. But basically what you would need to know from this is now you don't have a single point of failure. So if you are using PRP or HSR, essentially on your Ethernet network, all of the traffic is flowing in two different directions. And so if one of those directions like has any sort of failure, a switch dies or a cable gets cut, the information is still traveling in the other direction and it still arrives. So you have zero network downtime. So that's our solution for digital substations so that they can be used for critical infrastructure. So that's another really big aspect of 62850. I know we kind of glossed over that, but that's something I can do a whole 2-hour lecture on just PRP and HSR, so I don't want to get too far into it, but that's basically how we handle that problem of now we have our network as critical infrastructure. So I think this is the last slide I actually have. Oh, okay, I have 2 slides left for today. We'll kind of do a review of this next class, so I'll just talk about this really quickly here before we end. This is another really big aspect of people's concerns with 62850 is before you didn't really have as many cybersecurity concerns with your protection itself. So you could have your cybersecurity concerns on the more SCADA side that's going to your control center. And theoretically, you could like cut the hard line or whatever in terms of a cybersecurity risk, and your protection is still operating correctly, unless your IEDs themselves get compromised. But now with 62850, with digital versions of your hardwired signals, so we're actually like your analog and your binary IO, If you have an attacker on that network, then they can cause a lot of really bad things to happen very easily. So like the whole idea of cybersecurity risk has become very, very heightened from that. So we'll talk about that a little bit more next week, but that's the last kind of thing I wanted to get across with digital substations in general is you do have to think about that aspect is you can't really hack a hardwired signal, but you can with anything that's digital. And so if we digitize all this information, it's a whole nother attack vector for attackers to go after. So in terms of a digital substation, we have a lot of different attack vectors that we need to mitigate, basically. So for example, one of them is actually our time synchronization that I mentioned. What we do with that is we have a clock that synchronizes to GPS and then sends what time it is with PTP on your Ethernet network. There are actually attack methods of spoofing GPS to lie about what time it is. So then you can make it so that the clock sends out the wrong time to all the IEDs. They don't know that it's the wrong time. And so we have different mitigation techniques. And this is something that was actually implemented in Ukraine because that was actually being used to attack their substations. And also, like spoofed binary signals or spoofed analog waveforms would be the really big ones for a digital substation. All the same attack vectors that exist for a conventional substation still exist with a digital substation. It's just these are the additional ones that are even more of a concern. So we do have mitigations for them. I'll talk about that next time, but I think we're right at the end of class right now. We are. So any questions before we finish it up for today?
This clock, I mean, system clock, due to any reason, if down or didn't work correctly, so how that affect the equipment, the digital substation equipment?
So in the event of losing time synchronization, the relays would do something called blocking protection, which basically means they turn off their protection settings. So like, for example, if they're doing like differential protection where you need to compare different signals for that, they would stop doing differential protection entirely. So you would not have that protection. They could theoretically still do protection that only needs a single signal, like doesn't need to be compared to another one. So they could still do like overcurrent. So it's not like the end of the world, but definitely if we lose a clock, we're going to block some of the protection and we have downtime. And that's something I'll talk about again next time is the different standards we use, like KD Safety, where basically if you have downtime, then the utility gets charged money or they get fined by the government for it. So that's one of the big reasons we don't want to ever block protection if we can avoid it. So yeah, a clock being down would be bad.
Yeah, thank you.
Mm-hmm. Anything else? All right, then I will let you go for today. I'll stop the recording here.